In an ideal Brayton cycle with a regenerative heat exchanger, we know the input data to the devices and the efficiency of the regenerative heat exchanger. What is the heat consumed in combustion? What is the work generated by the cycle? In Thermonator, we configure a control volume exercise because the substance enters and exits the devices. We select the sign convention to consider the work generated by the system as positive. We also configure power units because mass has units of time. We could create the cycle quickly using the New Cycle menu, but in this exercise, we will create the processes one by one. We enter the pressure and temperature of the compressor inlet and calculate the state with those properties. The compressor performs an adiabatic process, so we create an adiabatic process. We enter the pressure of the regenerative heat exchanger inlet and calculate the state with this pressure and the entropy of the adiabatic process. The regenerative heat exchanger performs an isobaric process, so we create an isobaric process. We don't know the combustion inlet state, so we will calculate it later. The combustion performs an isobaric process, so we create an isobaric process. We enter the turbine inlet temperature and calculate the state at this temperature and pressure for the isobaric process. We select the Zoom menu to adjust the graph. The turbine performs an adiabatic process, so we create an adiabatic process. The inlet pressure to the regenerative heat exchanger is equal to its outlet pressure, since the regenerative heat exchanger performs an isobaric process. We enter the inlet pressure to the regenerative heat exchanger and calculate the state at this pressure and the entropy of the adiabatic process. The regenerative heat exchanger performs an isobaric process, so we create an isobaric process. We don't know the outlet state of the regenerative heat exchanger, so we'll calculate it later. We define the cycle mass as 1.74 kilograms per second by clicking the Calculator button. Selecting the Calculations menu, we see the equations used to calculate all the states and processes. We select the Heat Exchangers menu and the Regenerative Heat Exchanger. We select Process 5-6 and see that the energy balance is not satisfied because we haven't calculated the outlets of the regenerative heat exchanger. We enter an efficiency of 0.92. We calculate the enthalpy of outlet state 3 using the efficiency equation for process 2-3. We calculate the enthalpy of outlet state 6 using the efficiency equation for process 5-6. We see that the energy balance equation is now satisfied with the new outlet values, and we click Apply. We select process 3-4, that is, combustion. The solution is a heat consumed in combustion of 1420 kilowatts and a work output of 836 kilowatts. What is the purpose of the regenerative heat exchanger? We select the regenerative heat exchanger process, that is, process 2-3. We eliminate the regenerative heat exchanger by calculating the outlet with the same pressure and temperature as the inlet. We select process 3-4, that is, combustion. We see that the heat consumed has increased to 1582 kilowatts, and the work output of the cycle remains the same. That is, the regenerative heat exchanger heats the air to reduce the heat consumed in combustion. If you like this exercise, give it a like and share it with your friends.